We're now going to go over concavity of a function. Let's consider the following graphs that we have down here. You'll notice that each function is increasing or decreasing, but in very different ways, and this is related to concavity. In the first two graphs we have here, you notice that we have two increasing functions, but they're increasing in different ways. The first function we have here, we say it is increasing at an increasing rate. You see, if you move from left to right along the x-axis, at first you're increasing rather slowly, and that's related to the slope of your tangent line. Here the slope of the tangent line is rather small. Then as you move further to the right, you notice you're increasing more rapidly, and if you look at the slope of your tangent line, it's larger over here than over here. So the slope of your tangent line is increasing. If you look at the graph over here, you are increasing but at a decreasing rate. And that's related to the tangent line also. Notice that as you move from left to right, the slopes of your tangent lines are decreasing. So over here, the slope of our tangent line is larger than the slope of our tangent line further to the right along the x-axis. So here we say we are increasing at a decreasing rate. Now we give names to the shape of these functions. This function we say is concave upward. And this function, we call that, the shape of its graph, concave downward. We also have the same thing for decreasing functions. Notice this function here, we call this decreasing at an increasing rate. If you look at the slope of your tangent line here, it is a small negative number. And if you move further to the right, notice that the slope of your tangent line here is a much larger negative number. So you are decreasing at an increasing rate for this graph. As you move from left to right, your rate of decrease is picking up speed. You're decreasing at an increasing rate. Over here, you are decreasing at a decreasing rate. Notice the slope of your tangent line here is a larger negative number than over here. Over here, the slope of your tangent line is relatively small, close to zero. So we call this type of graph, we say that the function in this case is decreasing at a decreasing rate. Sometimes you'll hear these terminologies talked about in economics. If you have perhaps a budget deficit that is increasing, you might hear economists talk about it increasing at an increasing rate, which if it's a deficit would be bad, or increasing at a decreasing rate, which is good or better, because that means that increasing deficits are not good, but if it's at a decreasing rate, that means that you're getting control of it. At some point in time, it might actually start truly decreasing. So you'll hear this talked about from time to time. Down here, by the way, this graph is concave down. And this graph is also concave up, like this one over here. Alright. Now, let's come up with a precise mathematical definition for this concavity. Let's consider these two graphs down here. These will help us to determine a nice, precise mathematical definition for concavity. The first graph we have here is concave up. And let's take note as we move from left to right. Let's take note what happens to the derivative of the function. So keep an eye on this number right here as we move this point from left to right along the graph. So looking at the derivative of the function, it looks like our derivative is increasing. So our derivative went from, once again, it went from -3 to +3. And that makes sense if we consider the shape of the graph. Notice over here our slopes of our tangent lines are negative. Then they go to 0 right here, and then they start increasing. So they go from -3, increase to 0, and then go from 0 and increase to +3. So it looks like that might be a good definition for a concave up function, one in which your first derivative is increasing. Now let's see if that distinguishes it from concave down. If we look at a graph over here that is concave down, once again, keep an eye on what the derivative is doing as we move from left to right. So our derivative starts at 3, +3 now. It decreases to 0, and then it continues to decrease as we move along the curve. It's decreasing to -3 over here. So we see that our derivative is decreasing, and that seems to distinguish it from a concave up graph. And that is exactly what it's doing, and that's what we use for our definition for concave up and down. So here's our precise mathematical definition for concavity now. So we say that a function is concave upward on an interval if our derivative is increasing. That's exactly what we just saw. And a function is concave down on an interval if our derivative is decreasing. So that's our working definition for concavity. Now, how can we determine where a function is where a derivative is increasing and decreasing? Well, if you think back to when we were given a function f of x, and we were asked to find where does this function increase or decrease, we looked at the sign of its derivative, right? Well, now we're given the function f prime, and we want to find where it is increasing and decreasing. So we will look at its derivative. So in other words, we will look at the sign of the second derivative. So wherever our second derivative is positive and negative, that's going to determine where our first derivative is increasing and decreasing. And that's our test for concavity. So our test for concavity goes like this. Let f of x be a function whose second derivative exists on an open interval. If the second derivative is positive on that interval, then f of x is concave upward. In other words, this means the first derivative is increasing, and that means our original function is concave up. If, on the other hand, our second derivative is negative, then that means our first derivative is decreasing, and that means our original function is concave down on that interval. And that's how we're going to determine where a function is concave up and down. We will merely take its second derivative and find where it is positive and negative. So let's look at a few examples. So in this example, we want to find where this function, f of x equals x cubed over 3 minus x squared over 2 minus 2x plus 6, is increasing and decreasing. We want to locate all relative extrema, find where the graph is concave upward or downward, and locate any change in concavity. Now those are called inflection points, and we'll take a look at them in a little more detail after we do this example. So first of all, to find where this function is increasing and decreasing, remember we have to find where the derivative is positive and negative. So the first thing to do is set the derivative we want to set the derivative equal to 0 or find where it does not exist. Now, of course, does not exist. We don't need to worry about that in this case. So this is equal to 0. Now that factors as and so this has solution then x equals 2 and -1. Here are the critical numbers. So to find where the function is increasing and decreasing, we find where the derivative is positive and negative. So we'll do our sign pattern here. So we'll put in -1, 2, pick some test values in between like -2, 0, and 3. Put those back into the derivative and see if we get back positive or negative values. If we put -2 into the derivative, which is right here, that's the factored form of the derivative, we're going to get negative times negative, so that will be positive. If we put 0 into the derivative, we will get negative times positive, so that is negative. And if we put 3 into the derivative here, we will get positive times positive, and there we go. There's where we are increasing and decreasing. Now let's put that over here so we know that we are increasing from -infinity to -1 and from 3 to infinity, and decreasing from -1 to 2. We have some relative extrema here, so let's notice we have a relative maximum. That is right here at -1. That's where our function is increasing and then decreasing. So our relative maximum is at -1, f of -1. And evaluating this function at -1 gives us 43 divided by 6, or approximately 7.16, like that, and the 6 actually is repeating, so that's its exact value. So there's a relative maximum, relative minimum. That is right here. That occurs when x is 2, where our function is decreasing and then increasing. And so that is at 2, f of 2, which is 2 8/3, or 2.6, repeating like that. So remember now, this was the sign of our first derivative. Now we're going to have to find the sign of our second derivative. So to find where our function is concave up and down, that was the third part of this problem. We did the second part over here, so the third part of our problem now. We want to find where this function is concave up and down, so we need to find where the second derivative is positive and negative, so we take the second derivative, and we're going to get, and now we want to find where that is 0 or does not exist. So of course this implies that x equals 1/2. And there we go. So that is a critical number for our first derivative. That's where our second derivative is 0 or does not exist. And so now we want to set up a sign pattern for the second derivative. And we only have one point to mark off here, 1/2. And then just pick some test values on either side of that, like 0 and 1. And we put these numbers back into the second derivative. Be careful, these go into the second derivative. So if we put 0 into the second derivative, we get back -1. So our second derivative is negative on this interval. If we put 1 back into the second derivative, we get back a positive number. You get back +1. So our second derivative is positive here. And so therefore, we can now identify where our function is concave upward and downward. So the function is concave up. On the interval from 1/2 to infinity. And concave down on the interval from -infinity to 1/2. And this point right here is where we have a change in concavity. Now if we take that point, notice that we can put it back into this function, and that'll give us a point on the graph of the function where we have a change in concavity. That is called an inflection point. So the inflection point for this function is occurring at 1/2 f of 1/2 and if we evaluate 1/2, put that back into the original function, we get back 59 divided by 12, or 4.916, repeating like that. Alright, now we found everything. We found where our function is increasing and decreasing. We've identified relative extrema. We found where our function is concave up and down, and we've identified our inflection points. Now let's take a look at the graph of the function and see if everything here matches up with the graph. So here's what the graph of that function looks like. And it looks like we have a relative maximum right there, and that does look like it is at the point -1, 7.16 approximately. Right, there's about 7 on the y-axis, so that looks good. Right here we have a relative minimum that is at the point 2, and that's about 2.6, which is what we found. So that's at 2.67 approximately. So that looks good. And right here was where we have that change in concavity, and that does look like it's at the point 1, and we found it to be 4.916, and that right around 5, so that does look good. So that is at 1/2, 4.9 approximately. So that's where we have a change in concavity. And yes, it does look like, notice the graph is concave down from -infinity to 1/2. Right, there's 1/2. So that looks correct. Concave up from 1/2 to infinity. That looks good also. We are increasing from -infinity to -1. Then decreasing from 1, -1 out to 2, so that looks good. And then we are increasing from 2 to infinity, and so that looks correct. So yes, it looks like our graph is confirming everything that we found. Now let's take a look at, in a little more detail, inflection points. By the way, recall this point right here, that is where we have a change in concavity. We are going to call that an inflection point. So here's a precise definition for inflection points. A function f of x has an inflection point at a point c, f of c, if f of x has a tangent line at that point, and the graph of f has a change in concavity occurring at c, f of c. So here we have some examples down here. This graph right here looks like we would have an inflection point right about there, approximately. Notice that the function is concave down, then it becomes concave up, and notice it does look like we have a tangent line at that point. So that point right there would classify as an inflection point. If we look at this graph over here, looks like we have a change in concavity right there at 0, 0, concave up, and then concave down. Now, the one interesting thing to note here is technically the derivative does not exist at 0. And that's because our tangent line is actually vertical. A vertical line does not have a slope, right? So our derivative does not exist. However, the function does still have a tangent line at that point. It's just vertical. So technically this is an inflection point, because our definition up here said that at CF of C, the graph of f has to have a tangent line, and it does. Now, the derivative doesn't exist, but it does have a tangent line there, so that is an inflection point right there. This point right here, notice we do have a change in concavity here. We go from concave down, concave up right here, concave up, to concave down. Right there we have a change in concavity. However, technically it doesn't classify as an inflection point because our function does not have a tangent line at that point. The graph of the function has a sharp point or a cusp right here. So technically this is not an inflection point, even though our function does have a change in concavity there. Now if we look at this graph over here, we have a change in concavity as we move across 0 here on the x-axis. We go from concave down to concave up. However, notice that f of 0 in this case does not exist. So we do not have an inflection point for this function. Notice there's not even a point to plot on the graph of the function. So we certainly don't have a point on the graph where we have a change in concavity. Now we do have a change in concavity across 0, but we don't have an inflection point. So there are some graphs that clarify our definition of an inflection point. Let's take a look at a few more examples. So given this function, x to the fourth minus 4x cubed, once again, let's find where f of x is increasing, decreasing, locate all relative extrema, find where it's concave upward or downward, and locate any inflection points. So for part A, where it's increasing and decreasing, we will take the derivative and find where it is 0 or does not exist. The derivative of this function is and we'll try to factor that as and that does factor nicely. Now, where is that equal to 0 or dne? Well, clearly that's going to be 0 where this is 0 or this is 0. So setting each of them 0 individually, we get back that x equals 0 and 3, of course. There are the critical numbers for our function. So we'll put those on the number line and determine where our function is increasing and decreasing. So here's our number line. So this will be the sign f prime that we're looking at. And we want to mark off 0 and 3. And pick some test values like -1, 1, and 4. And we'll put these numbers into the derivative and see if we get back positive or negative. So if we put -1 into x here and here, we're going to get a positive number times a negative number. So the derivative will be negative on this interval. If we put 1 in for x, we will get a positive number times a negative number. That will also be negative. And then if we put 4 into the derivative, into x here and here, we will get a positive number times a positive number, so positive here. Now we can determine where our function is increasing and decreasing. So we are increasing on the interval from 3 to infinity. And we are decreasing from negative infinity to 0, and then from 0 to 3. And we can just write that as negative infinity to 3. You need to be a little careful sometimes when you have a situation like this. If 0 were a vertical asymptote for this function up here, then we would want to separate it out and write it as negative infinity to 0 and 0 to 3 like that, instead of like this. But this is not a vertical asymptote for this function. The function is defined here, so we can just write it as negative infinity to 3. Now let's identify our relative extrema. We don't have any relative max for this from this pattern down here that we see. That would require something like plus and then minus, and we don't have that, so we only have a relative minimum. And that is occurring at 3 when x is 3. So if we take 3 and we need to put 3 into the original function, evaluating 3, putting 3 in for x up here, we're going to get back negative 27 for f of 3. You can just check that out. Just put 3 in for the x up here. So that's where we have a relative extrema, and it's a relative minimum at 3, negative 27. Now let's find where our function is concave upward and downward. So for that part, we need to look at the second derivative and find where it is positive and negative. So we need to first take the second derivative and find where it's 0 or does not exist. So the second derivative for this, now we're going to take the derivative of this piece, not the factored form here. The second derivative is going to be and that factors as and we see that that is equal to 0 or dne at x equaling 0 and 2. So these are going to be the critical numbers for the first derivative, and that's going to determine where our function is concave up and down. So now we need to do a sign pattern technique for the second derivative. We need to find where the second derivative is positive and negative. So we'll mark these numbers off on our number line. And then we just need to pick some test values like negative 1, 1, and 3. And now be careful, we plug these numbers into the second derivative because we want to determine where the second derivative is positive and negative. Putting negative 1 in for x here and here, we will get back a negative number times a negative number, so that will be positive. Putting 1 in here for x here and here, we will get back a positive number times a negative number, so that will be negative. And then putting 3 in here for x, we will get positive times positive, and so that will be positive. So now we can determine our intervals over which we are concave up and down. So we'll be concave up. So the function will be concave up from negative infinity to 0. That's where our second derivative is positive. And we will be concave down. Oh, I forgot one other interval. Concave up also from 2 to infinity. And then we are concave down from 0 to 2. Now let's identify any inflection points. So we see we have a change in concavity at 0, And of course our derivative exists at 0. It exists everywhere, so this will be where we have an inflection point. So the inflection points are 0, f of 0, and that is 0, 0. So there's one inflection point. And then at 2, and then we need to evaluate f of 2. So 2, and that will be 16, if we put 2 in here for x, 16 minus 32, 4 times 8, so that will be 2 negative 16. And there, we've identified where our function is concave up, concave down, and we've found our inflection points. Now let's take a look at the graph of this function and see if everything that we've done here agrees with the graph. So here's our graph. Let me just erase a few things here so we can see it. So let's see, we have we identified a relative minimum at 3, negative 27, and yes, that looks like right about there it is. We identified inflection points at 0, 0. Yes, that does look like we're concave up here, and then we change to concave down. Also at 2, negative 16, that's right about there. Yes, that does look right also. We're concave down, and then we change to concave up. We found that our function was increasing from 3 to infinity, and yes, it is increasing from 3 to infinity. Also, it was decreasing from negative infinity up to 3, and yes, from negative infinity all the way up to 3, it does look like it is decreasing. Yes, that checks out. We found it was concave up from negative infinity to 0. So negative infinity up to here, yes, it does look like it is concave up. And from 2 to infinity. 2 to infinity, yes, it does look like it is concave up. From 2 to infinity. And concave down from 0 to 2. 0 to that point, yes, it does look like it is concave down there as well, from x equaling 0 to 2. So yes, everything looks like it checks out. Let's take a look at one more example. So if you'd like to try this one on your own, feel free to pause the video here. I'm going to continue with the answer. So we're given the function f of x equals x squared plus 1 divided by x squared minus 4. This is a rational function, a quotient of two polynomials. To save time, we're also given that the derivative is this rational function and the second derivative is this. Now you can check those out. You could evaluate the derivative of this by hand and you'll see that you get this, then take the derivative of this and verify that you get this as the second derivative. Now let's find where our function is increasing and decreasing. So we need to identify where the first derivative is 0 or does not exist. So where does? Well, that's going to be 0 when the numerator, negative 10x, is equal to 0. And that's when x is equal to 0. So it will equal 0 when x is 0. It will not exist when the denominator is equal to 0. And setting x squared minus 4 equal to 0, that means that x equals plus or minus 2. So that's where the derivative is 0 and does not exist. Now let's set up our sign pattern and determine where our function is increasing and decreasing. So and then we just have to pick some test points like negative 3, negative 1, 1 and 3, and we'll put these back into the derivative, see if they're positive or negative. So if we put negative 3 in here for x, we will get a positive number in the top, and the bottom is always positive, right? Because of that square right there, our denominator is always positive. So our first derivative is positive from negative infinity to negative 2. If we put negative 1 in here for x, we also get a positive number in the top, and the denominator is always positive, so we are positive here as well. If we put 1 into x right here, we will get a negative number divided by a positive number. The denominator is always positive, so that will be negative. And then if we put 3 in here for x, we will also get a negative number back. Alright, so let's see. So we are increasing. The function is increasing from negative infinity to negative 2, and from negative 2 to 0. Notice I didn't write this as negative infinity to 0, because this function has a vertical asymptote at negative 2. If we put negative 2 in here for x, we get 0 in the denominator, and we would get 5 in the numerator. That indicates that we're going to have a vertical asymptote at negative 2. So the function has a break at negative 2. So we want to write it, the interval, like this, and not as negative infinity to 0. We don't want to write it like this. So we do not want to write it like this. We want to write it like this. Now we are decreasing from 0 to 2, and from 2 to infinity. Notice once again we don't write this as 0 to infinity, because this function will also have a vertical asymptote at positive 2 when x is positive 2. Let's see, do we have any relative extrema? Well, we do go from positive to negative right here, so our function is increasing and then decreasing, so we will have a relative maximum at 0. Also notice 0, it's okay to put 0 in here for x, so we don't have any vertical asymptotes at 0. So we have a relative maximum at 0, f of 0, and putting 0 in for x, we get that is 0, negative 1/4, 1 divided by negative 4. So that's where we have a relative maximum. Now let's do concavity. So remember now, this was the sign of the first derivative. Now we need to look at the sign of the second derivative. So the second derivative is given by this function, so we want to find where does this function is 0 or does not exist. Well, let's see, the numerator, that is never 0, right? The numerator is never equal to 0 because we're looking at 3x squared, which is positive, plus 4, so this is always a positive number. So the only time it's never going to be 0. The only time it will not exist then is when the denominator is 0, and that is at plus and minus 2. So plus and minus 2. So those are the numbers we're going to have to put on our number line to look for the sign of the second derivative. So let's do that. So this is going to be the sign of f double prime. And so we have to mark off -2 and +2. And then just pick some test values in here, -3, 0, and +3. And we need to put these numbers, the test values, into the second derivative. So if we put -3 in here for x, now the top is always going to be positive, so we don't need to worry about that. So we would get a positive number divided by, now if we put -3 in here for x, we're going to get 9 minus 4, that's positive. So our second derivative is positive in here from -infinity to -2. Now if we put 0 in here for x, the top is positive. The denominator will be negative. 0 minus 4, that's -4 cubed. A negative number cubed is a negative number. So we will be, so the denominator is negative, positive over negative, so that will be negative in here. And then if we put +3 in here for x, once again that will be positive divided by positive. So, and there we go. So now that tells us where our function is concave up and down. So we are concave up on the interval from -infinity to -2, and from 2 to infinity. We are concave down from -2 to 2. Now let's identify any inflection points. Well, we see we have a change in concavity at -2, concave up to concave down. However, if we try to put -2 into the function up here, we see the denominator is 0. Right? Notice that f of -2 is of the form 5 divided by 0. So f of -2 does not exist. And the numerator, being a non-zero number, indicates that we're going to have a vertical asymptote at -2. So -2, while we have a change in concavity there, we do not have an inflection point. Similarly, we see that we have a change in concavity at +2. We go from concave down to concave up. However, if we try to evaluate f of 2, we have the same problem. F of 2 is also 5 divided by 0, which does not exist. Therefore, we do not have an inflection point at 2 either. So there are no inflection points. We do have changes in concavity, but no inflection points. So there, we found where we're increasing, decreasing, concave up and down. We've identified a relative maximum, and we see that we have no inflection points. Let's check out the graph of this function and see if everything matches up with what we found. Make a little room here. So here's the graph of our function. Notice we have vertical asymptotes at -2 and +2. From -infinity to -2, we are increasing and concave up. And so, yes, this is where we were. These two intervals were increasing. So yes, increasing from -infinity to -2. And we were concave up as well. From -2 to 0, we are increasing and concave down. And we see that, yes, from -2 to 0, increasing and concave down. Then from 0 to +2, we are decreasing and still concave down. So 0 to 2, decreasing, yes, that's what we found, and concave down. Then from 2 to infinity, the graph of the function is decreasing and concave up. And from 2 to infinity, yes, decreasing, and yes, concave up. So everything matches with the graph of this function. Oh, one other thing, right there is a relative maximum that is at 0, -1/4. And notice we do have changes in concavity, but we don't have any inflection points because there are no points on the graph where we have a change in concavity across. We have changes in concavity across vertical asymptotes, but those don't count as inflection points.